In this section, we're going to talk about something called the conditional probabilities and the multiplication rule. And we're going to see how we could use this to solve real world problems. So to begin, I want to do a little bit of introduction. So a little fun fact is that approximately 15% of adult men in the United States are more than 6 feet tall. So what does this mean? Well, if a man was selected completely by random, then the probability that that person is more than 6 feet tall is 0.15 or 15%. But what if you knew something about this person? What if you learned that this person that was selected is a professional basketball player? And typically, professional basketball players are way taller than 6 feet. So with this extra information, we know that the probability that this man is more than 6 feet tall is actually going to be a lot bigger than 0.15. And if you actually do the probability, it's almost going to be certain that he's going to be over 6 feet tall. And this is something called a conditional probability. Is a probability that we computed with some sort of additional knowledge. So, definition here, a probability that is computed with knowledge of additional information is called a conditional probability. And this is going to be the theme of this section. And we're going to do a lot of examples of these kind of probabilities. Let's go over some more definitions and notation. So here, a conditional probability is a probability that an event will occur given that another event has already occurred or has already happened. So let's say if A and B are two events, then the conditional probability of A given B is written like this. So how do we read this? If you see something like this, you read it as the probability of A given that B has already occurred or as B has already happened. So if you like to think about it, this little line here means given. So it will be the probability of A given that B already happened. And we're going to do a couple examples how to compute these. Let's say you have 4 people. It's Joe, Sam, Alyssa, and Maria, and they're running for student government. One person has to be chairperson and the other has to be secretary. How they're going to do this is they're going to put their name in a hat, and the first person randomly chosen will be chairperson and the second will be secretary. So our goal is to determine our sample space or all possible outcome. So we're going to think about this logically. So what if Joe was picked first as chairman and then Sam was picked second as secretary? Also, let's say Joe was chairperson and then Alyssa was secretary, or Joe could be chairperson and Maria could be secretary. What if Sam was chosen first? Then the possible outcome would be Joe would be secretary, or Alyssa would be secretary, or Maria might be secretary. And you kind of do this pattern for the rest of them. So let's say Alyssa was chosen first. So the possible secretary will be Joe, Sam, and Maria. And then let's say Maria was chosen for chairman. And so the only choices for secretary would be Joe, Sam, and Alyssa. So now we have a total of 12 possible outcomes. And now we can compute some probabilities here. So what is the probability that Joe is the secretary? If you look at our table, there's only 3 possible events that could happen. So the probability of Joe being a secretary is 3 over 12. or 1/4, or 0.25. But what if, suppose that the first name selected for chairman was Maria? Then we want to know what is the probability that Joe is secretary. So another way you can think about this is going to be the number of outcomes where Maria is chairperson and Joe is secretary, divided by the number of outcomes where Maria is chairperson. Let's look at the chart above, and let me get rid of these highlights. We want to consider when Maria is chairperson. So we don't consider all these other columns because Maria is not chairperson. We only consider this column. And we want to consider which one is where Joe is secretary. Is here. So it's 1 out of the total of 3. So in this case, it's 1/3, or 0.333. So this is an example of a conditional probability because we were given some knowledge or extra information to compute our probability. Our extra information was Maria was first selected. So notice that the probability of Joe being secretary is different than the probability of Joe being secretary given that Maria was first selected as chairperson. They're two completely different answers. And notice that this answer has a higher probability than this. And the reason is because since Maria was already chosen as chairman, we reduced the total number of outcomes to just 3, and there was only 1 chance where Joe could be secretary. And we can actually use a little formula, which is here. So let's say you want to compute the probability of B given that A already happened. Well, the little formula we could use is the probability of A and B over the probability of A. And notice that we can't compute this if the probability of A is equal to 0 because we can't divide 0. That's undefined. And another way you can think about this is that let's say all of your outcomes in your sample space was equally likely, then your conditional probability would be the number of outcome corresponding to A and B over the total number of outcome corresponding to just A. Let's consider the following consistency table. And we are already familiar with this table because this is what we've been working from the previous section. So all we have to do is fill it out. And again, if one way to check if you got it right, if the total number is the same as the total number of employee, then you're good. We want to find the probability of picking a person who is in favor given that they're male. So one thing you want to note is that because we only want to look at the male employees, our total number of employees goes down. It actually goes down to the number of just male employees because we're dealing with conditional probabilities. And so this new total, this is the total that we actually care about. So to compute this probability, the probability of a person in favor, given that they're male, is the number of male in favor over the total number of males in the company. So if you look at our chart, there are 15, and then out of 60, or 0.25. Let's consider this problem. When we want to find the probability of picking a female, given that they're in favor of the policy. So one thing you want to know is that the total that we care about here is the total number of employees that are in favor of the new policy. Another way you want to think about it is that the total that we care about is the given part of the probability. So in favor is the I part. So then computing this probability is the number of female who are in favor of the policy divided by the total number of employees who are in favor. And if you look back into the chart, the total female who are in favor are 4, and the total number of people who are in favor is 19. So then the answer is 0.2105. But remember, we have to round to 3 decimal places. Another thing I want to talk about is something called the general multiplication rule. And what this is just another way to compute the probability of A and B. And one way you can compute this is just multiplying the probability of A times the probability of B given A. And similarly, we could also do probability of B times the probability of A given B. And we're going to go over some example using the general multiplication rule. Let's say you're applying for a particular job, and the probability of being granted an interview is about 0.1. And among those people who got an interview, the probability of being offered a job is 0.25. We want to find the probability that an applicant is offered a job. Let's consider this sentence first. So another way you can think about this is just saying that the probability of being offered a job, given that you already had an interview, is 0.25. So this is actually a conditional probability because the actual information is that you already got an interview. So then the probability of getting an interview is 0.1. So this is not a conditional probability. So then you want to compute the probability that you get offered a job. And this, using the general multiplication rule, is just the probability of getting an interview times the probability of offered a job, given that you already took the interview. But we already know these values, so we just have to plug them in. So this will be 0.1 times 0.25. And the answer should be 0.025. And notice this is an extremely small number. So you have a low chance of just getting offered a job without getting an interview than actually getting the job with an interview. And this makes sense because nobody ever just hire you for a job without giving an interview. So that's why the probability of you getting a job with an interview is a lot higher than just you getting the job without an interview. Next thing I want to talk about is something called independent and dependent events. So here, 2 events are said to be independent if the occurrence of one event does not affect the probability of the occurrence of the other. And if these 2 events are not independent, then they are dependent events. And there's some couple properties that you want to know. So let's say event A and B are independent. Then you can say that the probability of A given B is just the same as the probability of A. And the probability of B given A is just the probability of B. Let's consider some examples and determine whether they're independent or dependent event. So suppose you have 2 fair 6-sided dice, and you're interested in the event observing 1 on the first die and observing 1 on the second die. So then notice that the first die does not affect the second die whatsoever. So then that kind of tells you that these 2 events are independent, because one event doesn't affect the other event. However, let's consider a college student was chosen at random, and the events are being a freshman and being less than 20 years old. So this is actually not an independent event. The reason for that is because one affects the other. So if the student is a freshman, then the probability of that student being less than 20 years old is greater than for a student who is not a freshman. Let's refer back to the example we did earlier with the 100 employees. So we want to know the events employee selected is male and employee selected is in favor of the policy, are they independent or dependent events? And remember, if something are independent events, then that formula is true. So we could say that let M represents the employee is male, and I represents the employee is in favor of the new policy. We want to check that if the probability of person is in favor of the policy, given that they're male, is the same as the probability of the person who are in favor, then we could conclude that the events are independent. So let's check. So if we do the probability of a person who are in favor of the policy, this is just saying that the number of employees who are in favor divided by the total number of employees. So in this case, it will be 19 over 100. And so the probability of a person who is in favor of the policy, given that they're male, this is just a number of males in favor divided by the total number of males, which is 15 over 60. And so notice that these two numbers are not equal to each other. And so since these two numbers are not equal to each other, we could say that these two events are not independent. We could also say that these two events are dependent. One thing I want to talk about is sampling with and without replacement. So when we do some sort of sampling from your population, you could do it one of two ways. You could do sampling with replacement or sampling without replacement. And sampling with replacement just means that when you select your individual from your population, you're able to place it back so it could be chosen again. However, sampling without replacement means that when you select your individual from your population, you have to remove it so it can't be chosen again. So in other words, there's no repeat. And one thing you want to note is that when you do sampling with replacement, these draws are independent, and when you do sampling without replacement, these draws are not independent. Let's consider the following example. So suppose you have 6 marbles, 3 greens, 2 blues, and 1 red, and you want to draw 2 marbles at random without replacement. So that's the key thing. And we want to find the probability that the second draw is green, given that the first draw was not green. So if you want to visualize this, let's draw like a small bag, and there are 3 green marbles and 2 blue marbles and 1 red marble. If we pick one at random that's not green, let's say this is blue marble, and since this is without replacement, we take it out. So there's total of 3 green marbles left out of 5 because we reduced the number of marbles. So in words, sampling without replacement means that the marble on the first draw is removed. So therefore, the probability of you drawing a green marble on the second draw, given that the first draw is not green, is 3 out of 5, or 0.6. But what if we want to find the probability that the second draw is green, given the first draw was also green? So let's draw a little bag again with 3 green marbles, 2 blue marbles, and 1 red. And since the first draw was green, let's say we pick this green marble, since we're doing without replacement, that marble is not put back, so it's gone. So now we have a total of 2 greens out of 5 marbles. So in words, we could say that sampling without replacement means that the marble on the first draw is removed. So therefore, the probability of the second draw is green, given that the first draw was also green, is 2 over 5. Because there's 2 marbles out of 5, or 0.4. Now we want to know whether these draws are independent or dependent events. And there's a couple of ways we could figure this out. we go through the definition route, so if we recall that the first and second draws are not independent, or another way of saying this is dependent, because the probability of drawing a green marble on the second draw depends on the outcome of the first draw. So if you go back to the definition of independent, this is what it means to be not independent. Another way you can think about it is that since we're dealing without replacement, we automatically know that these draws are not independent. So we could also say that since we are dealing without replacement, these draws are not independent or dependent. Not independent and dependent are saying the same thing. So let's consider the same problem A through C, but in this case, we're going to do sampling with replacement. And that's going to change things a little bit. It's actually going to make things a little bit easier. So let's consider a bag with 3 green marbles, 2 blue marbles, and 1 red marbles. Let's say we take out 1 blue marble, but since we're doing with replacement, we actually put it back. So the number of marbles stays the same. So there's 3 marbles in a total of 6 marbles. So the probability of you getting a green marble on the second draw, given that the first draw was not a green marble, is going to be 3/6, or 0.5. And it kind of goes the same thing for B. If we take out a green marble, since we're doing a replacement, we put it back, so it actually stays the same. So the probability of drawing a green marble, given that the first marble was also green, is also going to be 3/6. So it's a little bit easier. Now we want to consider whether they're independent or dependent events. But since we know that we're doing with replacement, we know that these are going to be independent events because one does not affect the other. So a great question to ask is that, let's say you know that you're dealing with an independent event. How does that change the formulas that we learned from this whole section? How does that change the multiplication rule, for example? So the multiplication rule for independent events, so let's say A and B are independent events. So the multiplication rule actually changed a little bit. So if you want to find the probability of A and B, and you know that A and B are independent, this is just going to be the probability of A times the probability of B. And it kind of goes with the extension of this. So if you want to find the probability of A and B and C and go on and so on, this is just the same as the probability of A times the probability of B times the probability of C. But why does this happen? Well, since we know that for 2 events to be independent, the probability of B given A is equal to the probability of B. And if you go back to the original formula, this was supposed to be the probability of B given A. But since this is this, all we're doing is substituting in. So that's how we got this formula. And there's a lot of great application with this. For example, suppose you want to draw 3 cards at random with replacement, and this is the key thing, because with replacement kind of tells you that you're dealing with an independent event. So let's say you want to draw 3 cards at random from a standard deck of cards, and you want to find the probability of drawing 3 kings. So we're going to use the multiplication rule for independent events. So you could say that to find the probability of drawing 3 kings is the same as the probability of the first draw is a king times the probability that the second draw is a king times the probability that the third draw is also a king. And since we're dealing with replacement, all of these probabilities should be the same. So since there's only 4 kings in the standard deck out of 52, this should be 4/52. And this number should be the same for all three probabilities because we're dealing with replacement. This should be 64 over 140,608, which is about 0.0005. And this is a really small number, which makes sense because picking three kings randomly from a standard deck of cards, it's a very low probability that you could do that. Another example will be, let's say you know that the percentage of people under 18 in New York is 23.5%, and Chicago is 25.8%, and LA is 26%. And let's say if you choose one person, what is the probability that all of them are under 18? And we want to see if this is an unusual event. We're going to use the multiplication rule again for this. So this is just the probability of choosing a person in New York times the probability of choosing a person in Chicago times the probability of choosing a person in LA. And we already know these values, so all we got to do is plug them in. But most importantly, we got to identify if this is an unusual event. And since this is less than 0.05, this tells you that this is an unusual event. So in words, we could say that this is an unusual event if we applied the most commonly used cutoff point, which is 0.05. And just to recap, the reason why we know this is an independent event is because it doesn't matter the individual from where we're choosing from. So this person, it doesn't really matter if this person is from New York, from Chicago, from LA. We're just picking one random person. Okay, so I know that we've been talking a lot about mutually exclusive and independent events, and very commonly people get a little bit confused about these two. So there's a little map here that hopefully could help you identify whether you're dealing with something that's mutually exclusive or independent. So you want to ask yourself first that does the occurrence of one event prevents the other event from occurring? And if the answer is yes, then this is a mutually exclusive event. But let's say the answer is no, then you want to identify whether you're independent or dependent. So then you have to ask yourself, does the occurrence of one event change the probability of the other? And if you know it does, then the event is neither mutually exclusive nor is it independent. But if your answer is no, then your event is independent. So hopefully this little map here kind of helps you out to identify mutually exclusive and independent events or dependent events. And here's a little summary of what we've been going over from this section and the last section. I know we talk about a lot of formulas here, so I actually made a little summary of some of the formulas that we talked about just to help you out on the exam. Lastly, I made a couple of practice problems here, and these practice problems are kind of similar of what you're going to expect from the exam. So what I actually recommend is try to do this on your own first, and I'm going to post up the solution and you could check your answer and see if you're on the right track.